Welcome back. In this first video for lesson 11, we're going to give an introduction to directional derivatives. To do so, let's recall the general paradigm that we've been using to construct derivatives. Recall from our discussion of both ordinary and partial derivatives that we define a derivative as the slope of a tangent line to some curve. Curve is really important because the way that we define the curve matters in our interpretation of the derivative graphically. Remember that in order to construct a derivative, we used a 5-step process. Step 1 was to graph some curve that is related to the given function. Step 2 was to find 2 points on the curve and draw a secant line through these points, where secant, of course, meant through 2 points. Step 3 was to measure the slope of the secant line through these 2 points. Once we did that, we completed step 4, which was to transform the secant line into a tangent line using a limiting process. And then, the last step of the process of constructing derivatives was to take the limit of the slope measurement. In other words, take the limit of the secant line slope to produce the tangent line slope. We called the slope of the tangent line that was created by these 5 steps the derivative of the original function. Let's do a quick review of how this worked in the 3 cases we've seen so far. We had this concept of an ordinary derivative. So if we have some function, capital F, from a domain in the real numbers into the real numbers, this means it's a single variable real valued function. We started with step 1, which was to graph the function as a curve. We then had 2 points on our curve, which are a f of a, x f of x, and the reason that there were ordered pairs is that this function was single variable. Once we had those 2 points, we plotted the line through those points, which we called the secant line. And then we measured the rise over the run. Once we did this, we let the x point approach the a point in the domain so that our second point approached the first point in the graph. And then we measured the limit of the slope as the derivative. Well, here is the slope of that secant line, rise, f of x minus f of a, divided by run, x minus a. And then here we've done some mathematics to transform the secant line into a tangent line, and we've measured the limit of that slope, and we call that the derivative of f at a, and that would be the slope of the tangent line running through this point. Of course, we had this nice, beautiful, wonderful algebraic trick, which was to set h equal to the difference between x and a, which implied that x was given by a plus h, and this was an algebraic convenience that let us take limits more easily, which led to this equivalent definition of the derivative. This is called the difference quotient. This thing was designed to prove theorems related to how to take derivatives. And then finally, we had this kind of fun mechanism to say that the derivative of a function f at a is the ordinary derivative of x, of f of x, ordinary because it's one variable, and then we use the evaluated bar at x equal a. So this is read the derivative of f of x with respect to x at the endpoint x equal to a. This was the ordinary derivatives, and we see all 5 steps available there. Now let's take a look at partial derivatives. In partial derivatives, we change one major assumption, and the change in the assumption is that instead of using a single variable function, we started with a multivariable function. We started with the easiest case, which was a 2 variable input, 1 variable output. Again, we did the same thing. We started with a surface When step one of the derivative process is to graph a curve, and so we made some simplifying assumptions depending on which type of derivative we wanted. If we wanted the partial derivative of f of x, y with respect to x, we set y to be constant, and then we looked at the intersection of the y equal b plane with the surface f of x, y. This was called a trace, and this trace is graphed right her. I like it when you graph it right her. And then we let the x values vary in the domain space. So this is now a set of points in R2. And what we did is we took a look at the rise over the run of the secant line through these points. So here we have a secant line. We had a curve. We've graphed 2 points. Here this point would be a, b, f of a, b. Here this point would be x, b, f of x, b. And then the rise over the run would just be the change in the output divided by the change in the input. This was quite easy to calculate because the change in the output was just given by this height. So f of x b minus f of x a, there's this height. And then because we held y equal to b constant in the domain, the change in from this point to this point in the domain space was just x minus a. We then translated the secant line into a tangent line by taking the limit, and we measured the slope of the tangent line to be the limit of the slopes of the secant lines. And recall that this related to this diagram in the graph, which is a 3D diagram, this related to a limiting path in the domain where we took a point P, x comma b, and we let it go to P naught, a comma b, along the line y equal b. So this is quite kind of subtle. This equation up here, y equal b, was the equation to a plane because it was in the 3-dimensional output of the graph. This equation, y equal b, is related to a line because we're just focusing on the domain space. Of course, we did the same algebraic convenience by setting h equal to x minus a. We flop this thing into derivative notation, which makes it quite easy to take limit definitions. And then this would give us the partial derivative of f with respect to x at the point a, b. That's how we read that symbol. We knew that this was with respect to x because we were letting x vary and we were holding y constant. And we could do this using the derivative operator notation. This right here is read as the partial derivative of the function f of xy with respect to the variable x evaluated at the point a comma b. So again, this was one of the partial derivatives, and it came from the same 5 steps. Graph a curve, find a secant line, measure the slope of the secant line, transform the secant line into a tangent line by taking a limit, and then measure the slope of the tangent line as the limit of the slopes of the secant lines, and then do some algebra to make it beautiful. Let's do a quick review one last time of the last type of derivative that we saw, which was not a derivative with respect to x, but it was a partial derivative with respect to y. We do the same 5 steps. We start by graphing the surface, intersecting that surface with the plane x equal a. So this equation is a 3-dimensional equation. It has 3 coordinates, a, comma, 0, comma, 0. And then when we intersect that plane with the surface, we get this curve. Of course, step 2 is to graph 2 points on that curve. So the first point is a, comma, b, comma, f of ab. Of course, this is not ab, this is f of ab. And then the second point was a, comma, y, comma, f of ay. The equation x equal a is a trace that produces that curve. And then what we do is we measure well, first of all, we draw a secant line through those 2 points. We measure the slope of that secant line, which is given by the rise over the run. So here, the change in output would be the second point minus the first point in the output space. So this is f of ay minus f of ab divided by y minus b. The reason that this length was y minus b is because we held x equal to a constant. We do the same thing again. We do the algebraic simplification where we set h equals y minus b. That gives us the derivative notation here. This partial derivative comes from looking at the path x equal a in the domain and then letting our output point go towards our given point along that path. And this was the way that we constructed the partial derivative of function f of xy with respect to the variable y evaluated at the point a, b. If you wanted to be fast and efficient, you could say that this is, of course, lowercase, so sorry about that. This is lowercase f sub y at a, b. Okay, so this gives us the mechanisms that we use to construct the three types of derivatives that we've seen so far: ordinary derivatives, and then partial derivatives with respect to x and y. Of course, we could do partial derivatives with respect to z if we had a 3-variable function. In lesson 11, we're going to flip the script, and we're going to talk about something called directional derivatives. So far, we've studied partial derivatives in Math 1C. And in partial derivatives, we moved along a very specific path. For the partial derivative with respect to x, we moved along the path r of t given by some point plus a direction. We're going to define this direction to be a unit vector, because if we do that, when we find the run, it becomes much easier. And we've already done this in the past part of this video. So here, when we were finding the partial derivative with respect to x, we moved along the x direction, and we held y constant. When we took the partial derivative with respect to y, we traveled along the path x equal a, which corresponds to a parametric equation given by a comma b plus t. So here we're holding a constant, and we're moving through the point AB in the direction of y, in the direction of 0, 1. In each case, we chose a very, very special unit vector in the pure direction of the type of change that we wanted. Here is the kind of amazing thing. In this lesson, what we're going to do is change the direction that we're moving. Instead of in the 1, 0 or 0, 1 direction, we're going to find this in any direction. So the idea of a directional derivative is to find the slope of a tangent line to a surface at an input point, AB, where we move along a line in any general direction. So here, the path that we're going to travel in the domain space is given by a point plus a parameter times a direction. The point stays the same, AB, but the direction is no longer a pure x or a pure y direction. It becomes a general direction, u1, u2. We're going to assume this to be a unit vector. This is a majorly clever assumption, which you'll see in the next video why that's important. But what I wanted to show you was the path along which we're going to construct a derivative for directional derivatives. Here you have an input point AB at which we're going to find the derivative. You have a line through that point, which we'll call r of t for now. And then what we're going to do is we're going to construct a curve on the surface that comes from projecting this line onto the surface. Then we'll have 2 points on this curve. We'll draw a secant line through those 2 points, measure the slope of that secant line, take a limit to create a tangent line, and then measure the limit of the slope of the secant line as the directional derivative in the direction of u. And what I wanted to show you was this direction u is general. It's not along x, it's not along y, it's along any direction that you would like. If you're getting this idea, in the next video, we will show you all 5 steps of how to construct a directional derivative on a surface using this general direction u. Again, let me reiterate. When we think about the direction u, it has to be a unit vector, and this is to save a lot of headache later in the construction of these directional derivatives. All right, we've just set the foundations. In the next video, join me for the construction of directional derivatives. Are you ready to rumble? See you in the next video.